Chapter 3 is talking about atoms. We know that the atoms are the building blocks of matter. In this first section, I want to kind of look at a historical perspective and get sort of a historical view on what earlier civilizations thought of atoms, as well as bring into some more contemporary views, like 1800 type views, and hopefully in the end of this chapter, or I know in the end of this chapter, we'll be talking about contemporary models of the atom. Now, the atom, from philosophical idea to scientific theory. Well, we all know that discoveries have to start somewhere. And in chemistry, we go all the way back to the days of Democritus. Democritus was born around 400 BC. He's said to live between 400 and 460 to 370 BC. And he said, he was a Greek philosopher, and he said that all things, or everything, or matter, what we now call matter, everything is made up of small, tiny particles, or small individual pieces, called atmos. That's what he called them. He called them atmos, Greek word atmos. Aristotle said that all matter is continuous and did not believe in atoms. He said that everything is continuous. So this board, or the desk, the wood, and the polymer coating that your desk is made out of, is all made out of one continuous thing. There aren't any smaller pieces. That was Aristotle's view. Now, the one thing that we have to remember is back in the BC era, they did not do a lot of experimentation. They were more philosophical ideas. They would think about it, and say, this must be the rational explanation. So they had no way of experimenting. In terms of experimenting, alchemy started in about 700 BC and come all the way up to the 1700s. Alchemy was developed as a result of Plato's ideas. Now, Plato was another philosopher. He said that all matter is made up of four elements: earth, air, water, and fire. Earth, air, water, and fire. Now, they believed that if they could somehow manipulate these four elements, then they may be able to turn things into gold. That was the primary focus, or primary objective of alchemy, was transmutation. Metals are made of varying proportions of sulfur and mercury, is what they thought. They thought that if they could get these proportions of mercury and sulfur right, that they could produce gold. Now, we will say this about transmutation and alchemy. In alchemy, they actually were able to produce several beneficial things like medicines. Never have been able, they never quite made their gold out of sulfur and mercury, because they didn't quite understand nuclear chemistry, but they tried and they were very successful. As a matter of fact, medicine shops, or what we call pharmacies today in the United States, are called alchemies, or alchemists, in the United Kingdom and other parts of the world. Now, Jabir ibn Hayyan, a Middle Eastern alchemist, in his quest to make gold, he found various other things. He ended up dyeing fabrics, making fabrics waterproof, and he actually was one of our first metallurgists, and he was very successful in finding, or rather, in refining metals. Now, in the late 1700s, the study of matter, or the study of everything, was completely revolutionized by the invention of the triple beam balance, or not the triple beam, by invention of the balance scale. It allowed us to quantify these experiments that our early alchemists started using, which eventually led to the discovery of three basic laws of chemistry. The first law of chemistry is the law of conservation of mass, or matter. In 1782, by a French chemist called Antoine Lavoisier, he was working with oxygen and a urea. He observed that the mass of the reactants before the reaction and the mass of the products after the reaction were complete were exactly the same. So, during the chemical reaction, the total mass before the reaction is equal to the total mass after the reaction. Conservation means something can neither be created nor destroyed. So we typically refer to this, this is one you've probably heard for several years, the conservation of matter, the law of conservation of matter states that matter is neither created nor destroyed, but it can only be changed. Now, the law of definite proportions in 1799, and actually French chemist Proust, who we're about to talk about, and Lavoisier actually were competing fairly close, doing very similar chemicals. Proust tells us, or Proust observed, that the elements that compose a compound are always in a certain proportion, regardless of the size or source of the sample. So that means in order to have water, or H2O, you always have to have two hydrogen atoms bonding to one oxygen atom. It's definitely going to be the same no matter where you get your sample. It doesn't matter if you get your sample out of the Washita River or the Nile River in Egypt. Water is still going to have the basic structure of two hydrogen atoms bonded to that central oxygen. Examples of laws of definite proportions, again, what I just said. The mass ratio of hydrogen to oxygen in water is always 1 to 8. Remember, hydrogen is a very light element. We have looked at some of the masses on the periodic table. We've explored the periodic table. We know the periodic table tells us a lot of stuff. The mass ratio of hydrogen to oxygen in water is always 1 to 8. There's always going to be 1 hydrogen for every 8 units of oxygen. If a sample of water decomposes into oxygen with a mass of 48 grams, how many grams of hydrogen will be released? Well, I'm going to let you work that out on your own. That'll be a test question. The law of multiple proportions states that if 2 or more compounds are made of the same 2 elements, then the ratio of the masses of the second element combined with a certain mass ratio, or certain mass of the first element is always a ratio of small whole numbers. In other words, if 2 elements A and B combine to form more than one type of compound, then the mass of B, which combines with the mass of A, is a ratio of small whole numbers. That's just saying that if you're dealing with hydrogen and oxygen, we know that hydrogen and oxygen compose water. Hydrogen and oxygen also compose something else that we use or we may encounter in our everyday life, hydrogen peroxide. Water is safe to drink. Hydrogen peroxide, you do not want to drink hydrogen peroxide. We use it as an astringent to actually kill bacteria. We do not need to ingest that. Another example is carbon monoxide and carbon dioxide. We exhale carbon dioxide. Now, carbon monoxide is produced from car exhaust, different things. If we take in too much carbon monoxide, then we can actually go to sleep and die from that. Completely different. We're obviously not dying from what we're exhaling. We would die if we inhaled if we had enough CO2. We would not be in a good position. But we have 2 examples here of things that are safe for us and things that could harm us, made out of the same elements, but the law of multiple proportions tells us that if you have different things, they're going to have different proportions. So they're going to have many different proportions of the 2 elements. Now let's talk about John Dalton. John Dalton is one of my favorite because John Dalton was an English school teacher and chemist. And that's basically what I said. He proposed an explanation for these 3 laws of chemistry based upon the idea of elements and atoms. Remember, up until this point, we've had a couple of different theories. We've had a particle theory of matter, which came from Democritus, saying that everything is made up of tiny little particles, and a continuous theory of matter. Everything is made up of one big, long piece of matter, from Aristotle. Dalton looked at it from the particulate side. Dalton's atomic theory, let's take a look at it. Number 1, Dalton said that all matter is made up of tiny, indivisible particles called atoms. He kind of took what Democritus said with atmos and said, hey, let's call them atoms after that great philosopher. The second thing that Dalton said is that all atoms of the same element are identical. Those of different elements are different. So, he said, and this is kind of where we kind of there are several things in Dalton's theory that are a little bit shady, but we'll talk about what we've done to upgrade them later. He said that all atoms of the same element are identical, which is partly true. They must all have the same number of protons, and those of different elements are different. Obviously, they're going to have different numbers of protons, but we're going to talk a little bit later in this chapter what we can do with the different numbers of neutrons and electrons. Third part of Dalton's atomic theory states that atoms of different elements combine in small whole number ratios to form compounds. So we have hydrogen and a different element, oxygen, coming to combine in small whole number ratios to form compounds. That goes back to say that atoms are indivisible. We cannot take different sections or different parts of an atom and divide them. We can't have half of a hydrogen or one hydrogen atom combining with half of an oxygen atom to form water. It just doesn't work that way. They have to be in small whole number ratios to form these compounds. And the fourth statement from Dalton's atomic theory states that chemical reactions involve the combination, separation, or complete rearrangement of those atoms. So chemical reaction, you're not dividing them, you're just combining them in different ratios, you're separating them, or you're rearranging the atoms, which actually we hold near today. How did Dalton's atomic theory support the three laws of chemistry? Conservation of mass. Atoms are neither created nor destroyed. They are indivisible. Law of definite proportion. A given compound is always made of the same proportion of atoms. It doesn't matter if you get water from the Washita River or water from the Nile, you're always going to have two hydrogens and one oxygen to form together to make that water molecule. And the law of multiple proportions. In two different compounds made of the same elements, the ratio of the second atoms is always to the first atom is always a small whole number. Well, we can't take halves of atoms. We can't take to make a compound. In order to make a completely different compound or multiple compounds from the same element, we must have multiple proportions. We cannot have the same proportions coming together. Law of multiple proportions, law of definite proportions are two that work hand in hand. Dalton's atomic theory turned Democritus' idea of the atom into a scientific theory that could be tested by experimentation. Now, not all aspects of Dalton's theory have been proven correct. We're going to talk a little bit later about what's actually wrong with Dalton's theory. The theories have been modified by new discoveries.